you so much for this warm welcome. It's really an honor to be here. I'm very happy to join this group today. And thank you so much for the team, for the smooth and flawless organization, for an exciting event to which we have very much looked forward in the past months. So it took several months to bring us all here together, and I hope you will enjoy our time together. So thank you so much again for the introduction. My name is Daniela Paolotti, and I'm a senior research scientist at ISI Foundation, and I have the pleasure of being here with my colleagues. We have some hours today to spend together. I would like to keep the discussion really informal, so please feel free to interrupt if you have questions, if you have any remark or comment. I really would like this to be a conversation with all of you, since we are here to establish new collaborations, to get to know each other, so let's keep it super informal. But before we dive into our first session, I would like to tell you a bit about our institution, ISI Foundation, the Institute for Scientific Interchange. We are based in Turin, in the northwest of Italy, by the Alps, not very far from France. And our institution is a small private, non-profit research institution. We do basic and applied research. We have more than 40 years of history. And we focus mainly on health, immunology, mathematical modeling for infectious diseases, pandemics, but we also have a division of the institute working on applying the data science tools in humanitarian response context, for example, so the so-called social impact domain, and also work by applying artificial intelligence tools to health and infectious diseases. We are supported by the local bank foundation, so we have institutional local philanthropy supporting us, but also a lot of project research grants with the European Commission. And that's what really brought us here together with the Mahidol team. The team project, which is a project supported by the European Health and Digital Executive Agency, HADEA, which started in 2021, right in the heart of the pandemic, and it brings together partners from all over the world, of course, including Thailand. And it's a global network aimed at gathering expertise and data from almost 30 partners in several countries, with a strong focus on children and pregnant women health. And the idea is to really bring together cohorts, public registries, so a diverse set of data sets and experiences to tackle the variants of concern that in 2021 were rising and creating havoc globally. And with the Thai partners, we have Mahidol University and Chiang University, and we have the pleasure of collaborating with them in the scope of this project. Very briefly, the idea revolves around a few work packages that are focusing on bringing together data from the various cohorts of public registries from the partners across the world to feed mathematical models. And that's where our contribution takes place in the W4 modeling work package, where ISI Foundation has been leading the activities since the very beginning. And we really try to leverage some of the data sets that were created in DERBI to apply mathematical modeling frameworks in order to not only capture, for example, the transmission of various concerns in certain settings back in 2021, but also to evaluate some interventions and some other measures that have been put into And I think Verdi has been a quite eye-opening experience in the sense that, especially in Europe, we are quite used to working only with European partners, especially in the scope of research grants. But thanks to Verdi, we had the chance to really expand our network with a global breadth and to really exchange knowledge, expertise, experiences with partners from all over the world, including Thailand. So we are really grateful for this experience. I would like to mention that Verdi was coordinated by the University of Padua, Professor Carlo Giaquino, whom some of you have met in the Verdi meetings that took place around the years. Hopefully this will be really just one, the first of many other collaborations and many other interactions that we have the chance to explore together. So let's now dive a bit into the reason we are here. In the next hour or so, I'll try to give you a wide, even if not really exhaustive, overview of what it means to do infectious disease modeling. I'm pretty sure that already some of you in the audience have been exposed to this kind of expertise, but this is really a chance to show you what has been done in the past, I would say 2-3 decades, the domain of modeling infectious disease, and what are the opportunities also for future preparedness for the next pandemic that are really being created in this very moment by many teams around the world. Let's first start with a picture that unfortunately has become too familiar for many of us, which is the spread of COVID-19 that started at the end of 2019 and really became a pandemic in 2020. And I think it's the very first pandemic that has been broadcasted on the internet, on social media, on TV, on many other media outlets in a way that is definitely unprecedented with respect to previous situations. And I'm pretty sure that you all have followed previous pandemics, like for example the 2009 H1N1 influenza pandemic. You might have heard about this influenza pandemic. You might have heard of Ebola or other problems like Zika. But the COVID-19 pandemic was really the first one that, on one hand, affected the world on a global scale that was really unprecedented, and that made us familiar with some terminology, with some concept that until then only epidemiologists or public health people were familiar with. And so I think that this media exposure really brought us closer to some technical concepts, some ideas that are very normal for infectious disease modelers and that have become instead very popular and very discussed. Unfortunately, due to the fact that the disease was so widespread and so disrupting for our everyday lives. So, what does it mean to do infectious disease models? And I'm pretty sure that everybody in the audience has heard about the fact that infectious disease modeling is a way to abstractly represent how a virus or another pathogen spreads among the general population. And we try to segment the population based on their health status, whether they have not been infected, so that they are still, let's say, susceptible with respect to the disease. Then we have those who have been exposed, so it means they have interrupted and potentially infected with someone who is already sick. And then people who are actually sick, showing symptoms, and very likely already spreading the disease. And those who have been covered, they have experienced the disease, they don't have symptoms anymore. So this is a very simplistic and yet very powerful way of representing how a pathogen can spread among the general population. And of course, we will see in a moment how this abstract representation has to neglect many details, many realistic information, but it's still a very powerful tool because it can be mathematically described with equations. And this makes this tool powerful from an analytical computational point of view, because then you can somehow play around with these kind of tools. But why these models have become so popular during the COVID-19 pandemic? Not only the scientific community have used these kind of models a lot to assess the situation, do short-term projections of what was going to happen, provide scenarios, for example, about the effect of interventions or vaccination campaigns. But many politicians around the world have used the outcome of mathematical models to show that if interventions are not put in place in a timely fashion, the situation is going to get much worse. You see, our models will show that the curve, the epidemic curve, will go up in an uncontrolled way if we don't react very quickly. And so, as I was saying, for the first time, mathematical models have been popularized in the news, on the internet, and many of you have become familiar with this concept. And that's why we really would like, with this workshop, to provide some additional, let's say, context that might make the use of mathematical models useful for the scientific life of this group. But what are infectious models, actually? So you heard me mention susceptible, infected, recovered. You will hear a lot about SIR models throughout this workshop. But how did we, say, come to conceive this kind of approach? Well, you can think about infectious models as the same way you see weather forecasting. I'm pretty sure you are all familiar with weather forecasting. How does it work, actually? Well, it's a very modern luxury that we have, the possibility of using our phones to check whether in an hour it's going to rain, what is the probability of having a sunny day tomorrow, with a very high resolution in time, but also in space. You know that in Bangkok it might rain, but maybe right outside Bangkok the weather might be better. So we all give for granted the fact that we have predictions in real time with a very short time frame. And that's exactly how weather forecast works. We have lots of sensors on the ground, but also somewhere in the atmosphere. You are collecting data about wind, humidity, precipitations. And these sensor-based data informed very accurate models for, basically physics-based models for the creation of, for example, clouds or wind currents or whatever will affect the weather. And the interesting thing is that these models are mathematical models that are informed by data and that somehow can be written on a piece of paper or fed to a computer to simulate what is going to happen based on the data that we now have in the next half hour, 1 hour, or even 1 day, 2 or 3 days. Also, very interestingly, we have forecasting and predictions also for example, extreme weather events. Imagine a cyclone, imagine a hurricane. And it's possible to trace the likely trajectory of a hurricane with an accuracy that is quite high, and we have also the possibility of giving an uncertainty. For example, here you see the trajectory of a hurricane starting somewhere in the Pacific and which is likely to land somewhere in Southeast Asia. And the shaded area is the uncertainty, the growing uncertainty around the path of the hurricane, which becomes larger as the path is further with respect to where the data were collected. And that's exactly how infectious disease models work. We collect data, we create mathematical models of what we think is important for reality and for the phenomenon that we want to describe, and then we try to project and predict what is going to happen, keeping in mind that the uncertainty around our projections grows the farther we project in time and also in space. So I think that the metaphor of weather forecasting is super useful, but there is a super big difference. For hurricanes, there's not much you can do to change the path of the hurricane. The only thing you can do is to try to get out of the way, or reinforce your infrastructures to be prepared for when the hurricane hits. But for infectious disease models, we have many powerful public health tools. We are capable of putting in place interventions that are so powerful that we can actually change the trajectory of the hurricane. We can actually reduce the impact of the hurricane. And if you might remember at the beginning of the pandemic, many countries around the world, and I think Italy was the very first in taking this decision, decided to simply freeze the movements, the interactions, the everyday life of the citizens, really to try and stop the pandemic at its very beginning. And so that's where the differences between weather forecasting and infectious disease modeling stop being so similar, because for infectious disease modeling we have so many ways of affecting the phenomenon and controlling it that for the weather forecast is simply not. And so the rest of the talk, and also what you will hear from my colleagues, is a story of how mathematical models have been developed, how they can be leveraged to study infectious disease spreading, and also what it means to model interventions, to model the impact of interventions, and also the feasibility, for example, of interventions that have an impact on the phenomenon. So, in the end, mathematical modeling means capturing the most important and essential ingredients of what happens in reality. You transform them into mathematical differential equations that can be mathematically treated, but can also be fed into computers through numerical simulations. And then you do projections, outcomes, plots, and that's where also the interaction with the public health officers happens through the communication of the results in a way that is still scientifically robust, but also can convey the main take-home messages of the modeling work. And infectious disease models are a tool that has shown to be super powerful, because during an outbreak, very detailed data about, for example, situational awareness can help project what might happen in the very near future. For example, it helps to estimate the parameters of the new disease, the transmission capabilities of this new disease, which measures, for example, like quarantines might affect the spreading of the disease, and whether vaccines are available, and whether vaccines will mitigate this outbreak. So, infectious disease models can help during an emergency situation to assess the situation, project what's going to happen, and come up with interventions to mitigate the problem. But they are important also before the outbreak, for preparedness purposes. to, for example, simulate what might happen if a new disease, if a new pathogen arises, and it can help to simulate what's going to happen and what the reaction of the population of public health institutions might be with respect to a new disease. So it's also very important to never forget that mathematical modeling are important both in emergency and non-emergency times. And by now you might have guessed that people who design infectious disease models cannot be only mathematicians, they cannot not be only public health people. There has to be a dialogue across several disciplines. You need epidemiologists, you need public health workers, clinicians, but also we will see, you will need data scientists, computer scientists, designers to create visualizations that are powerful and can convey the right messages. So the key is really to bring diverse teams that can work together to create models that have not only an impact from a scientific perspective, but can also be leveraged from a public health point of view and communicated to the research community, to policymakers, but also to the general public. And also we will see how models cannot be one size fits all. You will always need to tailor your models to specific populations, specific needs, specific diseases. And this makes infectious disease modeling very interesting because you will always have to adapt your tools that even if the same set of mathematical equations that have been developed for a certain purpose, given the right data, they can be adapted to different contexts. So, you will see with the sessions that will come after mine that the standard epidemic modeling approach, as I also mentioned, is related to the famous SIR model. So, dividing the population, neglecting any individual information, for example, age, gender, location, in space, in time. We forget all about it, and we simply look at whether a person is still not infected, so susceptible, if it has been exposed, or is already infectious, and also if it's recovered. And this is a super simple, yet very powerful way to describe how a pathogen, it can be a bacteria, it can be a virus spreads among the general population. And this simple approach, for which you will see many more details, can also be extended to diseases like, for example, vector-borne diseases that are transmitted by mosquitoes, for example. The let's say, approach, the paradigm that you use for writing the mathematical equations behind this model is exactly the same, with some additional layers of complexity. And a very important number that goes together, and it's very simplistic but yet very important from a conceptual point of view, is the so-called basic reproduction number, R0, R0. And it's the number of secondary cases in fully susceptible population produced by a single case. So it means if I am infectious in a completely susceptible situation, how many other people, given some time, will I be able to infect on average? And you can understand that if this number is below 1, it means that my infection is not so dangerous, right? But if I am capable of infecting at least one person, or 2 persons, or 3 persons, on average, it means that each of us can multiply the infection by this number, making it making the infection very dangerous. And you can see this picture is taken from a movie which is called Contagion. It's a movie that was actually sponsored by a foundation back in 2011 in collaboration with the Centers for Disease Control. This is Kate Winslet, she's quite a famous actress. And this was an attempt from the CDC and other public health institutions to really raise awareness about how a pandemic can spread in the world and really affect globally the society in which we live. And here she was writing on a whiteboard the R0 of several diseases. For example, flu, you see, is slightly above 1. Smallpox is quite contagious and is 3. Probably the most infectious disease that we know is measles with an R0 that is in the ballpark of 2 figures, so very, very high. And this was a way to really summarize how infectious a disease is in a fully susceptible population, so in unrealistic situations, but yet it gives you an idea of how this can spread. And tied to R0 is the number of people that you need to vaccinate in order to somehow contain the disease. And it's this very simple number, P critical, which is 1 minus 1 over R naught. And it gives you the critical fraction of individuals on a fully susceptible population for a disease that has an R0 as a basic reproduction number that you need to vaccinate. Interestingly, for measles, for example, you see that is where R naught is can vary between 11 and 18, but it's still quite high nevertheless. It means that you need to vaccinate more than 90% of the population to contain the disease. That's also why, for example, in countries like the US, we are seeing a resurgence of measles because the rates of vaccination have gone below 90%, which is super high. So this is just to say that these are very simple but powerful numbers. They probably don't capture all the nuances, all the realistic aspects that are behind the spreading of a disease like measles, but still they give you the ballpark of the kind of interventions that you need to put in place in order to have an effective way of mitigating the disease. Here are some links that I put to a few papers that came out on nature methods at the beginning of the pandemic with some of these informations more in details and that you are free to check out. And so now we go a little bit more into what can be done with mathematical models. So we have seen the most simple of all, SIR, but of course there's more to this story. Infectious disease models are used to support decision making, so they are used to make predictions. And in order to do so in an effective way, they have to account for the complexity that is inherent to society. Of course, we cannot go to a policymaker telling them, oh, look, you need to, I don't know, vaccinate everybody based on an SIR model that is super simple and doesn't account for age, for differences in socioeconomic and socio-demographic aspects. So that's why mathematical models need to account for a lot of the complexity that is possible to capture in the society. But that's also not only why mathematical models are used. I have spoken until now about the operational aspects. If you have an outbreak, you want to be able to say what's the intervention that's going to affect the outbreak, but also you want to understand more about the physical phenomenon that is inherent in the spreading of a disease. And so infectious disease models are also very powerful research tools that can be used by the scientific community to really understand the physics, if you want, of epidemic spread. And for both these purposes, we really need to try and understand that there is a super wide spectrum of complexity related features that we can include in our mathematical models. First, we can start with the homogeneous mixing of SIR that we have seen earlier on, to to have an idea, the ballpark of, okay, what's R0, what's the super simple fraction of population that I have to vaccine to mitigate the epidemic. But can I say something more? How many people will in each age group, for example, be affected by the disease? Is it more dangerous for children, for elderly people, for vulnerable people which are immunocompromised? Can I say something more about the nuances in the population? Can I say something about how do I have to cut the interactions among the population to mitigate the epidemic? You will hear a lot about contacts, contact factors, interactions, how these can be measured and leveraged and modeled to understand how it is spread, but also to understand how interventions can be in place. But you will also hear a lot about travel and movement in space. So people interact not only one-to-one in face-to-face interactions, but also interact by moving from one place to another, taking a plane, taking a train, and bringing, unfortunately, the disease with us when we travel in space, both on a short range infection, but also globally. So we will see how, for example, the mobility on a global scale can really help shed light on how pandemic can travel around the world. And then there are models that also account for super detailed situations, like we will see agent-based models that really try to capture the essence of people going about their everyday life and going from home to school to work, and how this everyday life is, let's say, interplaying with the spread of the disease. Let's start with some more technical parts on which type of models we could use to study the reality we are interested in. So we will look a bit at purpose and rationale for model development, scope and generalizability, and relevance to policy. So, as I was saying, the final, ultimate goal of the model is really to capture what happens in reality from a very detailed perspective. How does the pathogen is transmitted? How powerful is the infection? How likely is that a susceptible population is invaded by the disease? And also, which are the interventions that are suitable for these specific modes of transmission? For example, if I am thinking about a vector-borne disease, not allowing people to go to restaurants might not have any effect on our disease, but instead telling people, for example, to spray with repellent or wear long sleeves might have an effect. So again, everything we design to model has to have a purpose or an effect for the kind of phenomenon that we want to study. For the questions that we have, a very simple model might be enough. As I said, how many people do I need to vaccinate? More or less, an SIR model would be enough. But if I have to tell the policymaker how many people in each age group or for certain socio-economic situations will be hospitalized, then I need much more sophisticated models. And also, mathematical models are not invented in a vacuum. So every time we come up with a new model, we should look in the literature if someone has already done it, to try not to reinvent the wheel, and really try and see what previous research in a certain topic has done. As I was saying, the scope is also super important. Sometimes the models are designed to answer public health questions or emergency situations. Other times, more theoretical questions, more theoretical research interrogations drive the creation of the model. So again, why a model is created is also very important on how the model is implemented. And when a accounting for relevance to policy is also important to do accounting for feasibility. So if I tell the policymaker, look, you will have to cut all the travel by flights 100% in order to stop a pandemic from spreading, this is feasible from a simulation perspective, but it's also, of course, impossible from a practical point of view. And so, when devising and designing interventions, one has to account also for policy relevance. If I devise any intervention, this has to be feasible in practice and relevant for policymakers. This is what I just said. In relation to how actual models are implemented, there are several considerations that we need to be doing. There are different approaches. A model, as I was saying, is based on writing a set of differential equations that capture in time, so in a dynamical fashion, the way the health status of individuals change in time. So basically it's like counting for every second or every hour or every day how many people from susceptible become infectious and from infectious becomes recovered. And the way you write these equations can be deterministic, so the process is purely deterministic, and once you have initialized your equations, you have the same mathematical descriptions every time you run your equations. Or they can be stochastic, so for example you can introduce some level of stochasticity or uncertainty in the way your model plays out. And we'll see in a moment how these two differ. You can have compartmental models aggregating groups of population based on the health status. You can have agent-based models where each individual with its own identity in terms of who they are in the society is followed in the simulation. And then you can have a different level of heterogeneity accounted for in the description of the general population. So, for example, what is the difference between deterministic and stochastic models? Well, usually deterministic models are usually adopted when you want to describe phenomena that happen at the population level, involving mainly the whole general population. And why do we use models and don't we rely on clinical trials, for example? Well, clinical trials are great. They are probably the best tool that we have to test some research hypotheses, but they don't scale up to the general population. And that's why you need to use models. And the deterministic aspects of mathematical models are usually what's used for interventions on large-scale populations, while stochastic models are usually used to capture what happens in smaller population. But this division is not really always strict, and we will see in a moment what it means. And then compartmental individual-based model, as I was saying, they're used to differentiate what happens, for example, at a global scale. You can simulate an SIR model for the whole human population, like 80 billion of individuals, but an individual-based model can instead only be done for example, a city or a certain part of the society, country even, but it cannot scale up to the general population. Also because you want this data to be as much data-driven as possible. And when it comes to representing population heterogeneity, as I was saying, an SIR model neglects many of the details that are, in the end, important for epidemic spreading. So I mentioned contacts. You will hear a lot about contacts. The way contacts patterns unfold among the population are highly heterogeneous. And for example, children interact among them and with adults in a way that is completely different than, for example, elderly people who have way less contact, way less diverse interactions, and so on and so forth. To the point that you can even include, for example, births and deaths in your model if you want to account also, let's say, diseases that affect the whole lifespan of an individual. So a deterministic SIR model looks like this. It's a set of differential equations where you go at the difference in time in terms of numbers of individuals referring to each health status. And what you try and see is to look at steps in time. It can be seconds, it can be hours, it can be days. You have to choose a step in time that makes sense for your disease. For example, for influenza, usually you try and simulate what happens from one day to the other, but even from 1 week to the other. Going to the level of seconds, it doesn't make much sense, because if I am ill now, I will probably be still ill in 10 seconds or half an hour. But if I'm ill today, I might be recovered, for example, tomorrow or the day after tomorrow. So choosing the right time scale is always very important. And why deterministic models are interesting? Because sometimes, if the model is simple enough, you can do calculations, you can do simplifications that will let you calculate some very important insights. For example, if you assume that you are at the very beginning of an epidemic outbreak and your number of infectious people is really low compared to the number of individuals in the general population, you can solve the system of equations that you have seen in the previous slides and see that the outbreak will start only if the ratio of beta and mu, which are two parameters, transmissibility and recovery rate for the model, is about 1. And this is done only if the model is deterministic and is in a very simple situation, like at the beginning of the epidemic. And yet, you can see that in this very simplistic condition, there is a way to calculate this so-called epidemic threshold. So, if your pathogen has a transmissibility that is above a certain value, then the velocity with which the pathogen invades the population is exponential. And that's where things become interesting. Because if it's exponential, it means that at each time step, the epidemic will be amplified by the exponent of the exponential. And if it's 1, it will stay more or less the same. But if it's 2, it means that today I have 1 infectious, tomorrow I have 2, the day after tomorrow I have 4, and the day after tomorrow I have 16. So this means that in a very short amount of time, things can explode. And that's exactly what happened during COVID. And this is done with the simplest model that you can think of in the most simple situation. But actually, you can do many sophisticated things with deterministic models. If you have equations that are complex enough to capture most of the reality of the phenomenon that you want to study, you can use quite sophisticated frameworks, like, for example, this one, to first generate a set of trajectories for your disease, for your scenarios, and then choose which one, based on the data that you have, will be the most likely to happen. And this is done especially for deterministic models that can be informed by distributions of parameters and will generate a set of scenarios from which you can choose which is the most likely to happen. So even deterministic models can be very powerful. But stochastic models can also be very interesting. So running a stochastic SIR model, it means that whenever I have an infectious person that gets in contact with a susceptible person, instead of saying, oh, this person has a probability X of infecting a susceptible, and then running the equations with this fixed probability, I toss a coin and I say, oh, okay, I toss a coin, it's a head or a cross. If it's, for example, head, okay, this person is infected. If it's not, the person stays like that. So it means that at every contact, it's not granted that the person will be infected, but it's based on a stochastic process, which is equivalent to tossing a coin or tossing the dice, for example. And so it means that in order to have, let's say, a realistic representation of what's going to happen, you need to run the model many times, and to somehow have a summary of what happens to your system that is statistically meaningful, because you calculate the average, for example, of how many people at each time step are infected. That's what it means to add stochasticity to your SIR model. And we see that this stochasticity is super interesting because, especially from a global perspective, the fact that you can run your simulation many times and have more or less the same thing happening all the time is super powerful for predictions. But when it comes to complexity, we have talked so far only about SIR, what happens in the general population when people more or less on average interact among them. But we know that we don't talk to each other all the time. We are not mixed in a room all the time. We talk to someone face to face, and then we go to another place and talk to someone else, and then we go home and we interact with our household, and then we go, I don't know, to the movie and we interact with someone. So the way human contact networks are happening in reality has a huge impact on the way infectious diseases are modeled. And so what was found in the past 2 decades, thanks to mainly also digital data, is that each person has a number of contacts that can vary dramatically over time, but also from one person to the other. And the distribution of contacts among the general population is not Poissonian, is not a curve. The average value doesn't mean anything. It's a power law distribution spanning the several order of magnitudes, meaning that the majority of us has in their everyday life between 5, 10 contacts every day, but some of us might end up having 200, 2,000 contacts, for example, in a week. Imagine people who work in school, in hospital, or who work in public transport, the amount of people they see every day. This means that when it comes to spreading an epidemic, not everybody is the same. And so how many people we encounter and we interact with has a huge impact. When you want to model this in a mathematical way, what you do is that the first approximation that you can do is that you can group the population based on the number of contacts that they have. You will have a group of people who have 5 contacts every day, and then you will have a group of people who will have 50 contacts every day, and then you will have a group of people who have 200 contacts every day. And for each of them, you assume that the way they interact with other people is homogeneous inside each group. And then you go back to your SIR model and recycle it for each population group, differentiating from the number of contacts that they have. And this results in writing equations that are definitely very similar to what I showed you, with the difference that you have to account for the variability in contacts. This is super interesting because it somehow affects the probability of being connected from a certain group that has a certain average number of contacts to a group that has a very different number of contacts. So what is the probability that if I am a person that on average has 10 contacts every day, I am at some point in contact with someone that has 100 number of contacts? This is the way to somehow mathematically represent the heterogeneity of contacts among the general population. And it is possible to show that for some approximations, again, at the beginning of an epidemic, when the number of infected people is still very low, and in certain type of contact networks, the epidemic threshold depends on the number of contacts that we have. So it's not only based on the epidemiological parameter, beta over mu, but it also depends on the variance of the number of contacts. So the higher the variance, the lower is the epidemic threshold, and in certain situations, in certain very large scale contact networks, the variance is so big that the epidemic threshold basically vanishes. This means that in very heterogeneous populations, if an epidemic is seeded in the population, there is no way I can stop it. The epidemic threshold is always reached, we are always around the epidemic threshold, and the epidemic will always invade the population. That's why pathogens are so effective in reaching humans, because the way we interact in real life, this is a mathematical abstraction, but it represents reality in a very effective way. And that's why it's super useful to show that when it comes to epidemics, putting everybody in lockdown is probably the only thing you can do to stop the epidemic. So simply tying, severing the contacts among people, because the epidemic threshold is basically zero. And you will hear more about this from probably Mattia later today. But when it comes to networks, they are a super powerful tool to not only describe the way people interact in their everyday life, as I was saying, but also how people travel in space. And it is possible to describe in a very powerful mathematical way how people move, for example, from one city to the other, from Bangkok to Chiang Mai, from London to New York, or even on a short range scale from one side of Bangkok to the other, via a bus or on a car or even on foot. And the networks that describe the way people move around in space are, again, heterogeneous networks like the ones that we can use for describing the contacts among the population. And there is a very powerful approach called the meta-population models, where you can couple, for example, compartmental models that account only for the health status of people, and you assume that that's what the models that are applied in a geographical region, for example, and then you use a network representation to simulate, for example, the movement of individuals from one geographic region to the other, and again, look at the dynamic of the disease in each geographical region. And that's exactly what has been used in the past 20 years to simulate the spreading of infectious diseases such as influenza, or you might remember the first SARS-CoV ended from 3, or the COVID-19 pandemic. Because the data that describe the global travel around the world are available. There is the possibility of looking at data in real time that describe how many people, for example, take a flight from Bangkok to Rome every day, how many tickets are sold, how many seats are occupied, how many flights there are every day, every week. And it's basically a snapshot in real time of how people move on a global scale. It's actually a database that you can buy, and it covers several thousands of airports around the world, and it couples an incredible amount of populations around the world. But what is special about these so-called transportation network? Well, even in this case, the network is highly heterogeneous. The average number of flights or connections doesn't make any sense to talk about an average number of connections, because the distributions, as I mentioned also for the contact networks, is power law. So it means that you have airports that are very small, and have 10, empty connections to other airports. And then you have the Bangkok airport, which has tens of thousands of flights of connections every day. And this network is super interesting because that's where the say spreading happens on a global scale. And it is possible to really couple compartmental model with these air transportation data to build a meta-population model that will tell you, well, in Paris people are mixed and the dynamic of the disease happens according, for example, to a susceptible infected recovery model. And then at each time step, persons, individuals from Paris who are either susceptible or infected or recovered can travel with a certain probability to other cities and spread the disease and become part of the local population and of the local dynamics of the disease in other population. And the idea is really, in a very simplistic way, to couple geographical areas through travel operators that describe how infected and recovered and susceptible individuals can travel around the world. I am simplifying a lot, but under the hood you will see in the next session that there are so many realistic ingredients, data-driven, that can make this framework super powerful when it comes to simulating what happens when a real pandemic hits and you want to project on a global scale what's going to happen in the next weeks or months. And so this opens really the way to creating, for example, scenarios for propagation patterns. Can I predict what's going to happen? If I simulate that an outbreak starts in South America at a certain point in time, can I predict in a statistically significant way what's going to happen in the next weeks or months? The answer is yes, exactly because of the high heterogeneity and intrinsic topological characteristic of the air travel network. And so there are several works that are cited also in these slides that you can look at that use the historical data from past epidemics, in particular SARS-CoV in 2003, to show that if you initiate, for example, an epidemic in Hong Kong and you simulate the spreading on the air travel network for the following 14, 30, 45 days, for example, in terms of importation of cases in the United States, what you get are representations of different runs, different realizations of the same phenomenon. But you might think that every time you initiate a stochastic process, the stochasticity is such that what happens in the following time steps is basically random, right? Well, the answer is no, because it can be shown from a mathematical perspective that the epidemic follows the so-called epidemic pathways. It's like the pathogen follows some sort of the backbone of the network. There are some highways along which the pathogen will always find a way to spread. And that's what makes the it's basically, we are very lucky because it means that we can make predictions that are statistically robust and meaningful of how a pandemic spreads on a global scale, thanks to the fact that the network is such that pandemics are predictable. And I invite you to read this paper that was done in 2006 by Vittoria Polizza, who was sitting here, and Sandro Spagnani, who is our president, who were really the first to show that when it comes to pandemic, we are quite lucky because even in a crisis, in a global crisis, we can still be able to do predictions and projections. So this was more or less the first, say, flavor of what you can do from a technical perspective. how you can implement deterministic, stochastic model. But what about the way you represent the pathogens, the way you represent the specific population that you want to categorize into states that are mathematically described? What are the possible transitions? So when it comes to compartmental models, how many ingredients, how many different compartments I can create? Well, deciding which are the most important aspects that you want to capture in your phenomena is exactly what describes your compartmental model. You want to, for example, account for how many people not only recover, but those who become severe, or those who are hospitalized, and you have to create compartments that account for this. And people, for example, who are very sick and cannot travel, you have to account for those who travel less than those who are sick, but yet not so sick enough that they will stay home. So the way you represent your population really impacts the way you create your model. And also you want to be able to incorporate vaccine interventions or any other intervention in your model. You want to be able to really represent from a mathematical perspective this change in your system. And if you, for example, want to represent vaccinated people, you will have individuals among your susceptible that are a bit less susceptible. So for them, the transmission probability is a bit less. Or you want to have people who will stay home, and then for these people, you will have contact matrices, for example, that are slightly different than those who instead go to work or go to school. So the way you structure your population, your pathogen, or your account for intervention has a huge impact on the way you design your models, and also is heavily affected by the data that you have available. Because on one hand, you can create all the models if you want, you can be very creative and create models with 25, 50 parameters, but then you might want to have data to inform your models and make them more realistic. And so, deciding which are the key assumptions behind a certain model, and then dealing with the uncertainty related to these assumptions also has a huge impact. And this becomes super important when, for example, you want to design an agent-based model. As I said, you will still have your, let's say, compartments, you will still have the susceptible, infected, and covered individuals, but then at the level of details that describe how your agents, because we are really talking about individual agents simulated based on whether they are men or women or children, they live in a city or they live in a rural setting, or if they live in a condo or in a house, if they go to school or if they go to work. All these details can be accounted in an agent-based model, but the assumptions that you put in your model can really affect it. And there are several works that have been done in the past 15 years. This is quite a recent paper that actually describes agent-based models for virus infection that have been flourishing given the amount of data that are nowadays available, especially from a digital perspective. And especially thanks to improvingly better census data, you can create your synthetic populations that interact with their households, with their co-workers in a very realistic way, because it's based on census data that are very good and very realistic. I just want to mention a paper that came out for Italy around 2010, and that was called The Little Italy, and it's by Fondazione Bruno Kessler. They are our partners in Verdi, and it's a high-resolution agent-based modeling for the whole country, and it's based on very interesting data on time use. So there is a large survey that is carried out by the Statistical Bureau of Italy, in which a representative sample of the population is asked how they use their time every day. How much time they spend at home, how much time they spend at work, how much time they spend traveling. And this is done for a huge number of people, and based on this, you can infer how many people I encounter every day, at home, at work, and so on and so forth. And this is a way to construct very high resolution contact matrices, so the way people mix differentiated mainly by age, that can be used to inform the agent-based model. And you will hear a lot of mentioning of contact matrices. So I'm mentioning because the way you design your model and how it is informed by data such as, for example, contact matrices is super important. The Comics initiative is an initiative that was created in Europe during COVID, and it's a way to collect contact patterns through digital surveys in some European countries to really monitor how mixing patterns changed throughout the pandemic. And it was inspired by a project that was started back in 2008 with Polynode, which is now the gold standard when it comes to contact patterns for infectious disease modeling. But it remained the only data source that we had for many years about social mixing and contact patterns in Europe until Comics was done throughout the pandemic and was capable to collect detailed information about contact patterns in Belgium, in the Netherlands, in the UK, and also in Italy. This was led by our partner at Hassan University in the Andrea team. In the Italian let's say, experience of Comics, we were able to collect contact matrices throughout the lockdown of the winter between 2020 and 2021 to really show that between the pre-pandemic times and the lockdown times in 2021, the contact patterns had basically been completely suppressed. The way people interacted across different age groups completely changed, and it had a huge impact on the R0 of the COVID epidemic in Italy in 2021. These are three areas in which the regions of Italy were divided based on the severity of the epidemic and on the restrictions that were imposed in the various regions. And as you can see, for the red one, R0 was really suppressed thanks to the fact that people were put into lockdown. And we were able to measure this reduction with respect to other regions in which the restrictions were not so severe, thanks to the collected data by Comics. And this is really a typical example of how you can use a modeling approach to make sense from contact data with respect to the impact of intervention. More recently, there have been some theoretical works based on data collected, for example, in Hungary, high-resolution contact data during the pandemic, which tried to create contact matrices not only for age groups, but also for other socioeconomic dimensions. For example, unemployed versus employed people, people who live in rural versus urban situations. So how other socioeconomic factors can affect the way people mix in society, and also how can this become important for modeling. And another important source of data that you can use are mobility data. So we have seen how global scale mobility becomes super important when you want to study spreading. But if you want to study mixing, mobility data on a smaller scale are super important. We will hear more about this from Mattia. This is a work that was actually done by Nicolò in collaboration with Mr. Spignani, where they showed that by looking at mobility patterns in the city of Santiago de Chile and accounting for different socioeconomic situations in the city, could explain differences in the prevalence of COVID throughout the city, because not all the population groups could be compliant with the lockdown restrictions. Some, let's say, lower socioeconomic statuses didn't reduce their mobility during the lockdown in Santiago, and so this led to the spreading of the disease in a more, say, effective fashion than for population groups who could stay home and could be less exposed. On a, again, smaller spatial scale, this is a modeling study that was done by Vittoria Belizza, based on contact networks measured in school. And you will hear more about this by my colleague Ciro. This is a modeling study that tried to see the differences in screening approaches and interventions based on the screening for schools in France. And how these different strategies could lead to a different outcome. And the last thing I want to mention before we close is that eventually your models will not only have to incorporate real-world data, but will have to be compared in terms of outputs with real-world data. And that's where approaches like validation and calibration and using models for scenario analysis become important. And it has become so relevant that, for example, in the US there has been a huge effort in creating forecasting models for seasonal influenza every year. The CDC runs a challenge called the flu challenge that led to the creation of a group of modelers that every week submit their projections for the forecasting of influenza. But how do I make sense of 10 different models that have a slightly different outcome in terms of forecasting? And how do I compare it with the actual surveillance data? Well, on one hand, you have to calibrate your models based on the surveillance data from the past weeks. And then the projections, I cannot say this model is better than this other one, because it will vary across the season. One model will perform better than another, and then probably they will change. And so there has been a lot of effort in creating ensemble approaches to make sense of the different models brought together. And this led to the creation of the flu site forecasting hub in the US, to really invite people to submit their models calibrated on real-world data and whose performance is compared to surveillance data from one week to the other. Models can also be used not only to do forecasting but also to do scenarios. So based on certain assumptions, you will do projections that will help policymakers understand what might happen if, for example, you have a vaccination coverage for flu that is 60%, 80%, or 90%, what are the different outcomes. And again, different models can be brought together in these scenario modeling hubs to somehow distillate the results of each models under different assumptions. In Europe, we have a similar platform that was created right after COVID that we run at ISI. It's called Respicas, and it's a hub to encourage the modeling community to submit their forecasting models, again, calibrated on surveillance data, and whose outcome is evaluated individually but also in an ensemble fashion every week, where the ensemble model is also compared in terms of performance with the other models. Same goes for the scenario modeling. We also have, now it's been the second year, we have been collaborating with the European Center for Disease Control to design scenarios for influenza and COVID this year, and for RSV, the respiratory syncytial virus, for this year. And this is an effort led by Nicolo at ISI. The last thing I want to mention is related to data. Each model very nice theoretical exercise, but unless it's informed by data, it remains quite, let's say, standalone. I wouldn't say useless, because from a theoretical perspective it's still quite interesting. But data are really crucial to make models useful in an operational situation. And different models have different data needs. For example, simple compartmental models at the subpopulation scale can use surveillance data, contact matrices, and that's it. While for individual level and global scale data, you need to have, for example, global representation of the population or very detailed information on how individuals interact in their everyday life. So the kind of data needs that you have might vary a lot. And this means that also the kind of interventions that you can simulate for different models can vary a lot. And also the kind of data that you need to represent these simulations. And this is a nice paper that is with what I want to conclude by the team of NCORI, which shows the lessons for rescalable data collections. Based on the phase that you are in an epidemic, you will need to scale up your data collections. You will need better surveillance data to inform models that will tell you how transmissible is a pathogen. You will need data about the mixing of the population to understand if the mixing patterns have changed. You will need data about compliance with vaccination, compliance with interventions measures such as wearing masks or staying at home. So this data collection, so it's not possible to talk about modeling if you don't talk about data collections. And we'll see in the next session, but also throughout the workshop, how data are really at the heart of modeling. And with this, I will stop. If there are questions, maybe we can discuss them in the next